Okay, let's take a look at the single load network. All right, so top of the first page. Now, the source of this, you can see up here at the top, this is an article from a journal called Cognitive Science back in '02. And this fella, Chang, came up with these things called law encoding diagrams. So he developed them for electronics, he did some for probability and statistics, maybe some other things. And I found them quite interesting, and so I've put them to work in this course, and so I want to talk about this. And the reason why this is important, and the reason why it's in cognitive science, is notice that we have words, or we have words, symbols, and pictures. We have the words in the description. We have two kinds of pictures, the network diagram and this avow diagram. And the avow stands for amps, volts, ohms, and watts. So amps for current, volts for electric potential difference, ohms for resistance, and watts for power. Okay, so we're going to talk about how these all connect. And so right here, this network diagram, okay, we were just playing with more complicated versions of this. And so this is a resistor, R, and it's in a circuit. It would have some sort of voltage drop across it, either the entire battery or whatever chunk of the overall voltage it obtained in a larger, leaving leftovers for the rest of the circuit. There's always a voltage drop across the resistor in a circuit. All right? If there's no circuit, then there's no resistance. And so we have this idea that we've been pushing, that one way to think of electric potential is to think of the height, the gravitational metaphor for it. And so there's this voltage hill potential that it has. And we just worked out, or we were working with, Ohm's law, and that came out in lecture, and we just used it a few times in the circuit demos. But there's also power laws, and there are actually three of them. We're only going to deal with two right here. Voltage times, that should be current. That should be an I, not an L. So make that correction. I am not responsible for that typo. The authors of and editors of cognitive science screwed that one up. All right? Voltage times current, not voltage times length, is the power law. And then this other one, I squared R, okay, are the things. So there is a third one, might as well write it in, but it doesn't apply here because there's really no way to visualize this here, okay? So that's just true. V squared over R is another power formula. You'll read about that in the book, okay? But for our purposes, it won't matter much, right? So, but it is just generally true. And then we have this avow diagram, okay? And so let's think about this for a minute. It has a height V, okay? Same as over here, a height V for voltage. And it has a width I for current. And didn't we just the other day in lab make some graphs, voltage versus current? And we got a straight line graph. You should have in the lab that we were doing the other day. If you took a bunch of voltage readings and current readings, if you basic single resistor circuit, one resistor that doesn't change. You know, put in 10 volts, you'll have a certain amperage. Put in 11 volts, you get another amperage. If you did voltage versus current, you'd get a straight line graph, and its slope would be equal to the resistance. And so this box ends up letting us talk about how the resistance is this diagonal. So this matches what we would do with some graphical analysis. It also lets us talk about power as if it were area, because one of our power formulas is voltage times current, or the vertical axis, or the vertical length times the horizontal length. So I can treat power as if it were an area. So it's a geometric interpretation. It's not that energy or power is any more real than it was before, but just it's a geometric interpretation. And these will make more sense as we add more complexity to our circuits. But this is just the basics of what we're doing in this one. So kind of cut that one off. All right. So let's zero in on this next one. So now we have loads in series, okay? And we just did a little bit of that. So here's 2 resistors in series, and the first resistor would have a voltage A associated with it. The next resistor would have a voltage B associated with it. And the sum of those 2 voltage drops would be, if we were to continue this out, this would be the total voltage. Let me change my arrows. Okay, that would have to be the total voltage. 1 voltage plus the next voltage, it would have to add up. So voltages in series add up just like resistors in series. Okay, but that's because voltage equals IR, so we could add the IRs if we wanted to as well. So you can see right here that what we just drew in the network diagram models these 2 things exactly. All right, so total resistance is the sum of those, and total voltage is the sum of those. Those 2 things perfectly match the picture if we're thinking electric potential the same way that we think about gravitational potential, the height, the pressure that it would be under. Now, this right here is necessarily true because it's in series. It's one pipe, one path for current flow. The current through A has to equal the current through B because it didn't go anywhere else. There's no formula for that. That's just necessarily true by logic, conservation of energy, and charge. Those would be the scientific reasons, conservation of energy and charge, but just logically speaking, what else could it be? All right, it has to be that. And here's the thing, total power. If the power for one resistor was whatever it is, then the power consumed by 2 resistors would have to add, just like the voltages add and the resistances add. Okay, this would the power dissipated by a resistor, or the amount of energy per unit time that's eaten up by that resistor in the circuit, would have to remain that way. So just keeping things arithmetic, if you will. So now this last part. Notice that there's only one current. Okay? But there are 2 voltages. the voltages add, or in this case geometrically, we're stacking them. They're separate voltages. Even if they're the same voltage, they're separate. Because they're arranged in series, there's more total potential across both of them than if I put them in parallel, because if they were in parallel, they'd all have the same voltage height. But there'd be multiple currents, and current would have to add up. But since there's only one current, there can only be one current width. But there's multiple voltages, therefore I have stacking voltage heights. Okay? Now, let's take a look at resistor A, the first resistor. It has its resistance, and resistor B has its own resistance. And notice the slope of them. In this case, we've drawn them so that they have the same slope. All right? But if they didn't have the same slope, then one of them would have more or less voltage than the other. For a given current, if voltage B, if the resistor B had a higher resistance, its slope would be higher, but so would its voltage drop. Okay? But notice that the total resistance has a steeper slope than either one of the individual resistances. But wouldn't that make sense? Since I'm adding them, the total resistance would have to be steeper than the individual resistances. So the total resistance diagonal of the stacked voltage, or the stacked power blocks, if you will, has to be more steep, if you will, than either individual one. So far, the geometric interpretation keeps paying off. It's consistent. And really what this comes down to is this representational system, this geometric version of it, is it consistent with the way voltage and current and power work in a series network? And it is. So that's the trick about these sorts of things. They're useful when they're entirely consistent. And so far, so good. It's entirely consistent. Any questions about that so far? All right. This is not in any book that I know of. This hasn't made, why it hasn't made it to a book, I don't know. Probably because most physicists are not reading cognitive science. All right. A lot of physics education researchers do, but apparently not enough of them. All right. Let's go with this next one. So a parallel branch. So loads in parallel. And notice that resistor A and resistor B both have identical voltages on them. And we verified this in simulations, and we'll verify it again in real circuits when we do a lab this week. Okay? Any parallel network has one voltage, period. There aren't multiple voltages in a parallel network. There's one voltage. There's multiple currents, one voltage. Series network, multiple voltages, one current. And the reason for that is in a series network, there's one current, one path for current flow, but multiple voltage drops. But in a parallel branch, it has to be the opposite. There's multiple paths for current, but only one voltage. Okay? One pressure in the pipe, if you will, to give a water analogy. Now, here's where, I was supposed to use blue here. I'll fix that. All right. There's nothing obvious about that. Okay? Now, one thing is obvious, that adding resistance in parallel would require a 1/over approach. Nothing obvious about that. All right? We showed where that came from in a different lecture. It's just Ohm's law. because I have a total voltage, or I'm sorry, I have one voltage, and so more on that later. And then we've shown this product to sum rule, and which is great when we only have two. It works out super nice. And we've verified that the voltage has to be the same. All right, so these are things that this is way more obvious, and the other two things are not obvious at all. Of course, they're really just one thing, just different versions of the same thing. Now, total current would have to equal the sum of all the individual currents. That makes sense. That's Kirchhoff's node law. At work, it's just energy conservation. All right? And power would remain arithmetic. So this is a potentially sticky point, so let's think about that, because everything else is different, series and parallel, except for power. And that's because we're to get power is just energy per unit time. So if there's current flowing through something, it has a power value associated with it, and it's its own thing. And energy could care less whether it's in a series or parallel network. Power is power. It's energy per unit time through something. And so it remains an arithmetic sum, and all conservation laws are arithmetic. Sum of the parts equals the whole. There's only so much power in the circuit, and every individual part of the circuit is gobbling up some chunk of that power. Just like in your house. All those things are in parallel networks. Sometimes you have multiple things in series, and that might draw too much current, blow a breaker or something, too much power, energy per unit time going through a outlet or breaker or whatever. All right? So we have that. All right, so just want to be careful there. So now, notice that I have one voltage. Let's do this. I'll keep it in blue, since voltage was blue. One voltage. But I have two currents. All right? And there's two power blocks, VI blocks, if you will, going back to that power formula. But their height, they have to add in a different way. We were stacking them vertically when it was series, because there was one current and multiple voltages. Now I'm stacking them horizontally, because there's one voltage and multiple currents. And what that leads us to is that it's nice because now the total resistance has a less steep slope than either one of the individual resistors. And we just verified that in our last example in the other lecture with the actual circuit on FET. So now the slope of the total parallel branch is lower than any of its parts. Okay? And it could never be anything but the biggest it could ever be is equal to the smallest part, but that would mean because I would have some humongous resistor, you know, that would stretch it out and end up being the same as, you know, in the math there. Or the smaller resistor would stretch it out. If I took that IB, the second block, and stretched it way, way, way out, that means its resistance value is slope is going down, which means more current. And then it's the best that would happen is that it would get so flat that it equals the smallest resistor, that one, right? So far so good. Keeps delivering. It matches the way these two circuit options work out. So let's see here. I'm gonna skip that part, and I wonder if I can rotate that. So if we rotate that page, we can take a look at things. And what I want to do is kind of talk through this section here. All right, so let's first zoom in on this circuit right here. So we have this resistor A that is in series with this parallel branch and this other resistor. And technically, I'm going to put this parallel, so I have A in series with everything else. B and D are parallel to one another, and this chunk is parallel to this one. All right, so if we were to try to reduce this circuit, we'd have, you know, a number of steps to obtain a single total resistance for the overall thing, and it's all kind of laid out in a more complicated way than we've shown so far. All right, but we have this network here. And according to Kirchhoff's law, or just conservation of energy, which is actually, they're not supposed to be Kirchhoff's laws, they're Kirchhoff's rules, etc., but sometimes people call them laws. Current A has to equal something. And it's going to be the sum of everything that's coming into it. Okay? And it would have to be the sum of B, D, and E. So that one way to think about this node, so I'm going to pull this out here, that node, okay, would have, one way to think of it is in terms of IB, ID, and IE all coming into there and equaling current A. So one of the things that we'll get to, I'm not going to do them today, but we'll do some more circuits on Wednesday, and we'll apply Kirchhoff's loop and or voltage rule and the node or current rule, this is one we're looking at right now, to this. Is you pick a spot, a fork in the road, whether it has just 2 branches or 10 branches, it doesn't really matter, you pick that, that's a node. And one way to think about that node is all the gazintas have to equal, the sum of the gazintas has to equal the sum of the gazatas. And since there's only one gazata, the easy way to do that is to have everything go into that spot, the sum of those things has to equal the exit point. Could go the other way, but it's easier to do it that way. This is just conservation of energy, so I want to conservation of energy. The gazintas have to equal the gazatas. Now, let's take a look at total voltage. IA, let's do this. IA and RA. So this thing right here. There's a current going through resistor A. And there's a resistance value for resistor A, and Ohm's law says voltage is current times resistance. So total voltage would have to equal all of the individual voltage resistance product pairs. It would have to be that, okay? Now this next part, why would it only deal with, why do I get to ignore D and E in the total voltage calculation? Well, D and B have the same voltage, okay? And presumably E as well, even though it's not part of the parallel branch of BD. BD is its own little parallel network, but E is in parallel with it, okay? So there's a voltage drop here, and here, and here. All right? So we have this change, and that change. And so A, B, and C are the voltage drops, and voltage is always current times resistance. Okay? Hence, you have a current resistance pair, a current resistance product pair, and the last current resistance product pair. Which is why this statement here, total voltage is always going to be the sum of the current resistance product pairs. So this product pair plus that product pair plus that product pair. And the nice thing about it is when you have things broken up with parallel branches, you really only need the voltage, the current resistance of one of the things in the branch, because it will give you the voltage. Even if all the currents and resistance are different, the voltages will, the product pairs will always be equal according to the rule set. So that's decoding that a little bit. Now, I have to zoom out a little bit. So here's the thing. There's only one resistor, okay? Resistor A is the only resistor that feels the full current of the circuit. So remember, this is our voltage total, and this is going to be our total current. It always has to, if it's for the whole circuit, the vertical has to be the total voltage, and the horizontal has to be the total current. Okay? Notice that we had 1, 2, 3 currents at that first node. And I have a current width for B, a current width for D, and a current width for E. And the sum of those 3 currents is the total current through A. It's the same width as the whole box. So, still holding on, this is still consistent with the sum of the parts equaling the whole. And current has to be an arithmetic sum because it's conservation of charge. And all conservation laws are arithmetic, meaning a simple sum of the parts equals the whole, period, every time. So far so good. And also, you know, the voltage drop B and D are the same, but the voltage drop at E, not. E has got the voltage drop of the parallel branch of BD plus whatever C is. So it's feeling a full, well, almost full, everything but A. All right. And then you can see all the resistance values, and what wasn't drawn is a total resistance in this package, which in this case is going to end up being somewhere between the low and the high, because it was the parallel branch lowers what would otherwise be a series. Because if they didn't have that BD parallel branch, then it would be a higher, obviously, series adds up. But anytime you throw parallel stuff in, the total resistance now, so a series circuit will always have a total resistance that's the simple sum. It's no bigger than the sum. A parallel network, strictly parallel network, will always have a resistance that's no larger than the smallest one. And then logically, you would expect a series parallel combo to be somewhere between the low and the high. And that's because the parallel part is kind of pulling the rug out from under that sum, forcing it to be between the low and the high, somewhere between. All right. So this avow diagram, amperage, voltage, ohms, and watts, works out logically. It's consistent with the way the math works. It's consistent with the empirical results we would get in a lab, measurements, and we've seen all of those things in our simulation environment and analysis there. So that is the lecture, if you will, on the law encoding diagram, and there's some other things up here that I skipped over, and you're free to read those at your leisure.